So moving on from our last example where we'd found this class of even numbers, I'd asked myself, are there any odd numbers that might reduce to 1? And I really couldn't make any headway initially with this. I didn't know what I was doing. I was educated with engineering math, which is very different from, I guess, mathematicians' math. So after tinkering with stuff for a while, I decided to try to use one of the tools that I'd been taught in engineering math, which is binary. So I didn't know what to do, and I thought, well, I'll just transform some of these numbers into binary numbers. So binary notation uses only two symbols, 1 and 0, to write a number, and decimal notation, the normal notation we're used to use, is 10 symbols. So the reason you learn this as an engineer is because you're interested in computers. It's foundational for computers. So I thought maybe if I transform my numbers from decimal notation into binary notation, a pattern will appear, or I'll see something and I'll be able to figure out what, what is going on the odd side in the conjecture. So yeah, this is just a chart that's counting up in binary and decimal, right? So here you've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Everybody should know how to count that way. Binary, the numbers are a bit different, right? It goes 0, 1, and then you run out of symbols, so you got to shift over. Now you've got 1, 0 is 2, and then 1, 1 is 3, and then if you want to get to 4, you go 1, 0, 0, and then 5 is 1, 0, 1, and then 6 is 1, 1, 0, and then 7, and then. So one really neat thing that sort of pops out right away when you are doing this in binary is powers of 2, right? So powers of 2 in binary is a 1 with a string of zeros after it. And so this sort of ties in nicely to our last fact, which was that, the class of numbers that always reduces to 1 in the conjecture is powers of 2. So we can sort of see right away in binary why that's the case. You've got 1 with some string of zeros after it, going on. And since division by 2 in binary, if I'm going to divide a number by 2, so if I have 4, right, which is 1, 0, 0 in binary, and then I divide 4 by 2, I get 2, which is 1, 0 in binary. So division by 2 in binary is like striking off a 0, right? So again, sort of we can reprove what we just saw, which is that, any power of 2 will run down to 1 eventually, because we'll keep knocking off zeros. One other neat thing that you notice right away is that there are sort of 3 general classes of numbers. So there are powers of 2, which is some number with a bunch of zeros after it. Then we have all other even numbers, right? And these are a class of numbers that have some string of zeros, right? And then a 1, and then there'll be some pattern here. And the highest digit, of course, will be a 1. But you can see why if you take a number like, I don't know, say 10, right? That's 10 in decimal. And in binary, it's 1, 0, 1, 0. So you see that 0 there makes it even. And then there's some pattern here, 1, 0, 1, that is the rest of the numbers. So you can see again in binary, if division by 2, we've got powers of 2, which is a special type of number. And then we've got all other even numbers, which is a 1, some mix of zeros and ones ending with a 1, and then some string of zeros. And if we're going to start striking these off with the Collatz function, eventually we'll get to this odd number. We'll have some odd number here. So we have odd numbers, right? So odd numbers in binary is a 1 with some string of zeros and ones in it, and then ending in a 1. So we have 3 classes of numbers, and one of them, these even numbers, transforms into an odd number. So I've got one class here, right, where we know that we're good. This always reduces to 1 under the conjecture. And then I know that my other class of numbers transforms into these odd numbers. So all I have to do is figure out if there's a way to prove that all odd numbers reduce under the conjecture. So I've split my problem into 2, and I've solved one of the problems. So next I'll talk a bit about some more questions I asked with odd numbers. But I feel like this is a good place to stop for this second video.